So we're taking a look at quiz number 5 here. It says a 1,200 kilogram car traveling west 90 kilometers per hour collides with a 1,500 kilogram truck traveling north at 65 kilometers per hour. They head off, they entangle, they head off as one object after. And we want to find the velocity of the wreckage immediately after the collision. So we've got this 1,200 kilogram car, we'll call car number 1, going at 90 kilometers per hour. Do we want to convert that to meters per second? It doesn't matter, right? We can or we don't have to. Now, a straight momentum problem, we have to. Impulse, we have to. Conservation of momentum, because the units cancel, we don't have to. In the last class, I didn't convert it. I left it as 90 kilometers per hour. With you guys, I'll convert it to meters per second here. 90 kilometers per hour would be 25 meters per second. Then we got another car, car number 2, that has a mass of 1,500 kilograms, or a truck, I should say, that's going at 65 kilometers per hour to the north. What is that 65 in meters per second? Was it 15 point something? No, 18? 18.055. Thank you. They head off as one object after the collision. Hey, listen, if you're ever not sure whether they head off as one object after the collision, okay, it's okay. Okay, you can always treat it as two separate objects if you want. Okay, it's not a big deal. All right, we don't have any funny angles here, so we can go straight to our x components and our y components here, where pi is equal to pf in both cases. m1 v1i plus m2 v2i. First one we have is 1,200 times negative 25 plus 0. 0 because the second one is only on the y-axis, and we're analyzing only the x-axis here. That's equal to the total mass of 2,700 kilograms times Vf. Let's solve for the value of Vf there. 1,200 times neg 25 divided by 2,700. What does that give me? Thank you, Brendan. We'll do the same thing for the y component. Pi is equal to Pf. The initial momentum for object number 1 would be 0 on the y-axis. For the other one, object number 2, it's 1,500 times 18.0556 equals 2,700 times Vf. Brendan, what did that one equal? And that one is positive, as you can see here. Now we combine these. We go 11.1111 to the left. We go 10.0386. The resultant vector here, that's really what we're looking for, and the angle there, of course, as well. The speed, 10.0386 squared plus 11.1111 squared. Yeah, it's going to give me something around, I don't know, 11 point something. 12? 14, okay. 14, we'll go 3 digits, 14.96, or we'll go 15.0, I guess, right? 15.0 meters per second. And the angle, by the way, expressed as kilometers per hour, that would be somewhere in the range of 50 something. Did anybody do it in kilometers per hour? What'd you get? 53? Yeah, it sounds right. Sounds in that range. So we're going to mark both of those right. The angle here is the inverse tan function of opposite over adjacent. The opposite is 10.0386. The adjacent is 11.1111. So that's going to give me about 44-ish, I'm thinking. Somewhere close to 45 degrees. I don't remember what it was in period 1. Okay, 42.07. We're going to round that to 42.1 degrees. And it should be north of west. We won't take any marks off if they forgot the north of west. Okay, if their angle is consistent with the diagram, mark it right. By the way, they could have a 38 degrees west of north as well, right? As long as it's consistent with the diagram, we'll mark it right. We'll give 2 points for this question, guys. 1 point for the calculation of the speed, 1 point for the calculation of the direction. Jake? It should be 3 digits. No, I'll mark it right. If they did it right, mark it right. Yep. They just put 15 meters per second. Okay, why not do that? And why is it important to calculate the velocity immediately before the collision and immediately after the collision as opposed to several seconds afterwards? I saw some people with a really long answer for this. Really, all you need is a really short one, but the long one could still be right. What's the answer to it? Yeah. Yeah, it ensures that it's an isolated system. Okay. So basically, you might have said it ensures that it's as close as possible to an isolated system. You might have said there's no chance for external forces to act. Something to that effect. You guys getting the point? We want to have a reason for momentum not being conserved out. Let's give 0.5 for that one. Okay. If we want to have a reason for momentum not being conserved, external forces are the whole idea of an isolated system. Okay, that would be okay. Yeah, that would be okay. Yeah. Okay, hold on before you hand it back, guys, okay? Because there's a couple other things that I wanted to ask you here that I could have asked you on this quiz, and I just didn't. Okay, first of all, what if I had have asked you to solve for the final momentum here? What if I had have asked you to solve for the final momentum? I didn't. I asked you to find for the final velocity. But what if I had asked you for the final momentum? How would you do it? It shouldn't be very hard. Yeah. Okay, you got the velocity here, it's 15 meters per second. The final momentum would simply be equal to 15 meters per second, or the unrounded version of 15 meters per second, times the mass. Sorry, we go to the mass first, I guess. 2,700 kilograms, that's the total mass afterwards, right? Times 15 gives me whatever. And the angle would be the exact same, right? As the velocity, 42.1 degrees north of west. Got that, guys? So you want to find the final momentum, you got the final velocity, multiply it by the mass. The alternative would have been you could have found this momentum, and you could have done this with momentum as opposed to with velocity, and then just gotten an answer for final momentum right away. Another question I could have asked you. What's the initial momentum of this system? Who's got that one? What's the initial momentum of this system? What do we get, by the way, when we multiply 2,700 times 15? Let's put an answer down there. So my final momentum would be 40,500. What's my initial momentum? How would I find that? Actually, it looked like you were kind of ready to answer there, but then you kind of looked like you were kind of waving yourself off there. Have an answer? It's exactly the same. Okay, that's a ridiculously easy question if we think about it. Okay, if we're asked for the initial momentum of this system, well, you got the final momentum. That's the same as the initial momentum. You don't do any work for it, just write down the answer. And finally, what if I had have asked you whether this was an elastic or inelastic collision? There's something that can tell you right now without doing a calculation whether it's an elastic or inelastic collision. What is it, Stephen? Yeah, it's inelastic because they stuck together. Now, what if you didn't remember that? What if you had to find whether it was elastic or inelastic, and you didn't know that because they stick together that it's inelastic? Or maybe they bounce apart in another question. You've got to do a calculation to determine whether it's elastic or inelastic. I'm not going to go through that entire question with you, but I will show you how to set it up. We would say EKI is equal to 1/2 m1 v1i squared plus 1/2 of m2 v2i squared. The total initial kinetic energy. The total final kinetic energy, EKF, would simply be equal to 1/2 mvf squared because there's only one object. Now let's put some numbers in here. I don't even care about the answers, the calculated values. I'm just going to put some numbers in here and show you something that if you think about it, you'd be able to do right now yourself. But if you don't think about it, you might try to make it harder than it has to be. M1 would be, before the collision, would be, what was it, 1,200, I think? Yeah. 1,200 kilograms. What would V1I be? Let's look at our original diagram again. What would V1I be? Negative 25? Just put 25. Why would we put 25 and drop the negative? Why do I drop the negative on that, Tara? Good, good. Speed's a scalar. We don't need direction with it. In fact, not only do we not need it, we don't want direction with it. All right, let's do the second one here. Object number 2 has a mass of 1,500 kilograms. What am I going to put in for V2I? 0, right? Because that's on the y-axis, right? No, we're going to put in 18.05556. Why would we do that? Why can we put the x value and the y value all in the same equation? Couldn't do that up here, right? Up here, I had to separate them into x and y components. Down here, I'm just saying, don't do x and y components, just do it all together. How come, Tara? Again, same answer, right? Because it's a scalar. So not only does the negative here not matter, the up here doesn't matter either. Up, down, left, right, negative, positive, doesn't matter. 38 degrees south of west, it doesn't matter. When you're calculating kinetic energy, we drop the direction entirely. Get a number for that. Do the same thing for the final, right? Okay, the fact that it's at 42.1 degrees, who cares? It's just going to be 1/2 of 2,700 times the final speed of 15 squared. I don't care what direction it is. Get the number. You're going to find that the final ends up being less than initial, and you'd say that it's inelastic as a result of that. Okay, with momentum, you always have to do components if you're in two different planes, an x and y plane. Okay, with energy, kinetic energy, you don't. You treat it exactly the same way as you do those one-dimensional problems. Okay, it's the first time we've done one in 2 dimensions, right? Elastic / inelastic. But is it any different than it was for one-dimensional collisions? Not in the slightest. Not in the slightest. Okay, don't ever split kinetic energy into x and y components. There was a hand up over here a second ago. I'm not sure. No, it's up to you. That's up to you. Yeah. No, be careful. If they stick together, you don't need to calculate it because you know that it's going to be inelastic in that case. If they bounce apart, you don't know for sure. Now, if it's a car collision, I would bet $100 it would say it's going to be inelastic still, because you're still going to have squishing going on, right? Deformation of the car, which means you're almost certainly going to lose kinetic energy. But you got to do that calculation just to make sure, unless they stick together. If they stick together, you're safe in not doing the calculation. Okay? Unless it's Monday's test is multiple choice numeric response. You will have in a few weeks a momentum test in the middle of another unit that's a written response test. The reason we do that is because, I could give it all to you right now, but I figure like, you know what, in another month, you'll need some review for momentum because it'll have been a while. So we'll do that in another month or so. In a written response test, I might say, justify mathematically that this collision is inelastic or something like that. So if I say specifically to justify mathematically, even if they do stick together, you got to do the calculation, right? Yeah. No. Guys, be okay with this? The quiz itself and the questions that I could have asked you on the quiz? All right, let's head to the front of the rows, please. All right, let's give you a few hints for this test you got coming up on Monday. Firstly, there are 18 questions on this test. 18. 14 of them are multiple choice. 4 of them are numerical response. Not that that really matters to you, right? 14 multiple choice, 4 numerical response. Jake, last one is a numeric response question. And I'll tell you right now, that last one is a numeric response question that's a 2-dimensional collision with a funny angle. Okay, so you got to be able to do that. Okay, not a surprise, right? I don't think I'm really giving anything away that you couldn't have figured out on your own. Go figure. There's a question, there's at least one question where you have to do a 2-dimensional collision with a funny angle. Okay, of course you're going to expect that, right? Since Jake saw the back of the last page, we'll get that one out of the way first. The first couple questions are kind of qualitative in nature. Okay, I see impulse. I see conservation of momentum in one dimension. Surprise, surprise. I see more impulse. Oh, hey, I see a two-dimensional explosion. One of those questions where, here's the object and it explodes into, right, 3 pieces or 4 pieces or 5 pieces or 68 pieces. I'm not going to tell you how many pieces it explodes into, but I will tell you it's not 68 pieces. Okay, you could do that if it was. It would just be a lot of work if it was 68 pieces. It'll be 3 or 4 pieces that it explodes into. Okay, nothing crazy hard there. More impulse I see here. Well, there's a couple questions that actually say what's the impulse. That's great because you know what to do there. What's the other situation though where we use impulse? The other change in momentum, right? But what's the other main one? Sometimes isn't as obvious. Force and time. So there's a couple questions that say impulse here, okay? But it seems to me there's 1 or 2 that just mention something else as well, like force and time type thing. Oh, here's one. Here's a good one. Here's a graph. What kind of graph do you think you'd see on this test? Oh boy, you guys have some studying to do. What kind of graph would you see? If it's a force versus time graph, though, hey, what do you automatically think when you see a force versus time graph? 3 words. Yeah, area equals impulse, right? Now, if it's a graph that looks like this is easy. The area equals the impulse 1/2 base times site. If it's a graph that looks like this, it's a little bit harder because now we got to break it up into 2. Now we got to break it up into 2 sections. Two sections that would look something like this. Okay, we'll call this number 1, this one number 2. 1/2 base times height for this one, and base times height for this one. Easy enough though, right? What if we saw something like this? What if we saw a force versus time graph where it went below the x-axis? What would we do then? Well, this is still one section, triangle 1/2 base times height. This is still one section, 1/2 base times height. But what do we got to be really, really careful of in that case? Yep. Yeah, negatives. Something's going to be negative here, right? This area, we're going to make a negative value. So if this is 50 and this is 30, then the area here, the impulse would be 20, right? If the first one was 30 and the second one was 50, the impulse would be negative 20. Make sense? What else could I ask you there? Well, once you have the impulse, which is just simply the area, if you're given the mass, then you could easily find the change in velocity as well, or the final velocity given the initial velocity. Okay, there's an F versus T graph on the test. Okay, again, no real big surprise, I don't think. Okay, I'm going to ask you some of the things that I asked you here today. Okay, nothing more than what I've asked you right there. If you know how to do everything that I just described, you're fine for that question. You're more than fine, in fact, because I did more here just now than what you're going to see on the test. Okay. What else you got? Oh, here's a good question. Oh, I think I'll just leave that one. I think we'll just leave that one as a nice little surprise for you. Good question, though. Good question. I'll tell you that if on this question that I'm thinking of right now, it's not unlike a multiple choice question that you guys saw on the podcast Wednesday when I wasn't here. Okay, I did a multiple choice question. Okay, on the board, you guys worked on a multiple choice question. It's not unlike that multiple choice question in many ways. I won't say anything else about it. Oh, here's another two-dimensional explosion. There's 2 of them on there. What? Impulse again. There's not that many concepts here, right? What do we have? Just straight momentum. Then we had impulse. Then we had conservation of momentum. And then we had elastic and elastic collisions. And then we had two-dimensional stuff. There's 18 questions. There's only 5 real concepts, so of course each one of them is going to be asked more than once. Oh, here's a good one. Remember that variable value changing thing? When you triple the mass and whatever? Here's one of those. No, not more conservation of momentum. And here's a qualitative question. Here's a two-dimensional T-bone question like you had on your quiz, right? 90 degrees. Okay. Which, of course, we would expect to see on the test as well. Qualitative question. And then Jake's curling question. Two-dimensional collision with a funny angle involved there. This does not occur in this curling question. So I'm not trying to give you some special hint on this particular curling question, okay? But what if this did occur at some point? Okay, what would we do? Well, let's say we've got a ball number 1, it's got a mass of 2 kilograms, let's say, coming at 10 meters per second. Ball number 2 is at rest. It has a mass of 3 kilograms. Let's say ball number 1, after the collision, goes this way at a velocity of, I don't know. This wouldn't even work out mathematically probably because I'm just kind of making it up as we go here. Let's say the angle worked out to be 40 degrees. Object number 2 goes off this way and if you strike that head on, they're both going to go straight down, right? But if it's a glancing collision, then you can cause one to go one way, one to go the other way, right? It's pool. It's billiards, right? You hit a ball straight on, it goes straight. If you hit it on the side, they both go off in opposite directions, right? Let's say this angle is 50 degrees. Its mass, of course, is 3 kilograms. And we're trying to find the speed here. Okay, you could solve that problem, right? You got a funny angle. Wait, you got 2 funny angles. What are you going to do with that funny angle? That's 60 degrees there. Oops, I just gave it away. What are we going to do with that 60-degree funny angle? Yep. Change to what? The only problem is, yeah, I mean, it's a good idea. I don't like funny angles, right? So we want to get rid of them. So let's change it into an X and a Y. Like right over here, this green one, it's 40 degrees right here. And 6.0 meters per second, we can turn that into an X, and we can turn that into a Y using cosine and sine, right? We do this one, though. 60 degrees. Okay, this is X, this is Y, but we don't know any of the 3 sides. So what do we do with that? Well, if you're not sure, there is a shortcut that angle would allow you to take. But if you don't spot that shortcut, don't spend 10 minutes looking for a shortcut that's going to save you 1. Okay, if you're not sure what the shortcut is, just pretend you don't have it. Listen, if you got this question without the angle, which is what the last question on your test is, basically, then you could solve for the angle. You could find the angle. So you're given the angle. You don't need to be given the angle because you could find it. But if you are given, ignore it, right? Ignore it. But if you are given the angle and you spot the shortcut, okay, you can go ahead and take it. Here's the shortcut. Don't panic about this, though, okay? Because it's just a shortcut. It's nothing that you need to be familiar with. You never, ever have to take the shortcut. It's just that every once in a while it might save you 90 seconds of your precious time. Monday, by the way, time shouldn't be a huge issue because we've only got 18 questions in 78 minutes to do it, right? Should be able to do it in 54 minutes, 3 minutes per question. First test, though, will give you a little bit of extra time. Okay, we break this up in X and Y components, right? We get the X and Y for this one. We basically turn it into something that looks like this, right? We get a V2F here for the X component. I don't know what it would work out to be. It doesn't matter. You could go and do the Y component in the exact same way and solve for V2F for the Y component. And then you could combine them. by redrawing it as a right angle triangle, Pythagorean theorem in the inverse tan function, right? We've done that a bunch of times. You're going to do that on your test on Monday, on your last question. But what you could do, if you spot the shortcut, because you're given that angle there, you could not do the y component. You could do just the x component. Take a look at this again now. A few minutes ago, Lucas wanted us to resolve this vector right here, 60 degrees, into an x and a y, but we didn't know what the hypotenuse was, so we couldn't do that. But guess what? We now know what the x is, right? We just found it right here. So you could use sine to find the hypotenuse, which is really what we're looking for in this question, right? You could use the x component in sine to find the hypotenuse without going through the process of getting the y component and then the Pythagorean theorem and then the tan function. Does that make sense to anybody? Put up your hand if that makes sense to you. Okay? If it doesn't, that's okay. If it doesn't make sense, let's not spend time trying to learn a shortcut, really. Let's not spend a ton of time trying to learn a shortcut. Just do it the longer way. Okay, again, it takes you an extra 90 seconds. It's not the end of the world. Okay? I don't want you to get confused over a silly little shortcut. Okay? And who knows if you'll ever actually see that or not. I have seen questions like that in the past where they've given us that angle, okay, but most of them don't. I will tell you guys, that usually in a multiple choice question, that's a two-dimensional interaction, there is a shortcut usually. And the reason for that is because those two-dimensional collisions are pretty long questions, right? And as a multiple choice, they usually give you a little bit of a way to save some time on it. But like I said, don't spend 10 minutes looking for the shortcut that's going to save you 90 seconds. Okay? You just spend the 90 seconds and get it done, even if it has to be the long way. Fraser?
Would it be the y?
Say it again.
Would it be the y that's the length of the x?
Well, we solve for the x component of this vector, right? You could solve for the y component of that vector if you had have done conservation of momentum with y, right?
How do we get the x?
Well, pi equals pf, m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. Solve for v2f.
Aren't you figuring out the v2 for the left?
I'm sorry?
Aren't you figuring out the v2f for the left one?
No, because we have all those numbers already, right? We had this one was 6 meters per second, and then we just changed it into an x and a y. Those numbers were given to us, basically. Okay, this number was given to us, and then we just changed it into this and this. Okay, we don't want to find anything really for object number 1. The goal was to find the final velocity of object number 2. Well, we found the x component by breaking it up into the x and y components, and then we stopped and said, wait, we don't need to find the y component to get the hypotenuse, because if I have the x in the angle, I can get the hypotenuse directly from that. Any other questions about the test on Monday, guys? Oh, perfect timing. Okay, have a good weekend, everyone. Study hard. Hey, one more piece of advice, guys. Stop before you go. One piece of advice. As you're preparing for this test, there are 30-something multiple choice questions at the end of your Unit 1 worksheets. Okay, we've done a number of those multiple choice questions in class already. The ones we haven't done, you should do. They're not on the test, but they come from the same place. They're all old diploma exam questions. So they're good practice. Do the multiple choice questions, okay? Have a good weekend, everyone.